Hi, everyone. So I'm Andrey. Welcome. And my thingy stopped working, of course. It's misaligned. Give me 20 seconds. Whoa. OK, cool. It works. All right. So I'm Shazo on the internet, also that turkey, if you've seen me around. You might know me from such open source projects as YourLive3 and some amusing tweets I've made. So we're going to be talking about Go with Python, but it's not super specific to Go. All of these things you can do with other languages that are similar. But first of all, who here uses Go? Oh, cool. So like almost half of you, maybe a third. My favorite things about Go, the syntax is really simple. So you can get started in a few hours, and you kind of can already be helpful to other people. Learning it is really fast. The compiler is really fast. So normally one of the downsides of a statically compiled language is it takes a long time to build, whereas Go, especially small projects, they build in milliseconds. So you can kind of iterate as quickly as you would with an interpreter language, and it's statically compiled. It's statically typed, so you have more safety. So integers, strings are strings, and other types. Statically linked binary, so you deploy by just building a binary and just shipping it off to a server and running it. And it cross-compiles to tons and tons of platforms. They're adding new ones like every month. And at this point, they've gotten to the realm of like things I've never heard of before. So you can build from your Mac up to the Raspberry Pi to Linux, and it all kind of cross-compiles really easily. The concurrency is a very important feature of the language, especially these days and age where CPUs aren't really getting faster per core, but we're just getting more cores. Concurrency is becoming more relevant. So in Go, you just stick a Go in front of your statement. That makes it run concurrently. I mean, oversimplifying, but you know. And the standard library is super, super good. Like I know our lovely language here is known for having good standard library, but the Python one, oh sorry, the Go one is even better in my opinion, especially the HTTP library, which I'm kind of responsible for rewriting in Python. Go one is actually good out of the box. The crypto stuff is really good and really usable and reusable. I'm a big fan. And there's Gophers. So if you're into Gophers, there's those. So hypothetically, if you wanted for some reason to run Go from Python, maybe you have some code that's a coworker already wrote in Go, and it's really complicated, and you want to rewrite it in Python, or it's fast or something, and you want to run it from your Python code. This is how you do it. And that's it. Thank you. I mean, you could do that, and we've talking to a couple people about using inter-process communication and things like that, which is totally valid. But we're going to go into a little more fun territory. So as many of you probably know, Python can speak with C. So a lot of the modules you install from pip, like LXML and things like that, they come with C that is optimized, and it builds on install, or it comes pre-built for you. And Go speaks with C. In fact, it makes it even easier for you to speak with C. I'll show you some examples in a moment. So therefore, Python speaks with Go, right? And this is, as I said, these lessons, this is kind of be high-level strategies for dealing when you want to speak across two different runtimes. So this applies to any two language pairs that speak with C, so Ruby, Java, whatever. But when we're dealing with runtimes, we have to be careful when we're breaking through that barrier, because languages like Python and Go, there's garbage collectors and the global interpreter lock, and if you're using something that rewrites the flow of the code in real time, there's JITs and resource pools for Go routines. All these things mutate the state of your runtime, and when you try to share information across those runtimes, you're going to run into challenges. And the other challenge is some language constructs, unless you're passing very basic integers and strings around, your language constructs might not make sense across the language boundaries. So things like Go has interfaces and Go routines and channels, like how do you translate that into Python? And Python has classes and generators that doesn't really exist in Go. So you have to create these bridges abstractly to allow to speak cross languages. So here's our little runtimes. On the left, we have our little Go bubble where all of the Go ecosystem lives. On the right, we have Python with the GIL and the garbage collector. And this all kind of exists in this barren, beautiful wasteland of C, where it has an important property because C by default doesn't have a runtime. So the code you write in C is the code that kind of gets executed. There's nothing preventing you from leaking memory. There's nothing that's going to rearrange your stuff behind the scenes unless you do it explicitly. So C acts as a medium for us to do crazy stuff. So here's what we're going to build this We're going to walk through this talk. Here's how you run a web server in Go, okay? For those of you who haven't done Go, it's mostly self-explanatory. So there's a package main, which tells it when you build the binary, it's going to be the main entry point for the binary. And the bottom, we use the HTTP module to register a handler for the /URL. And the handler takes two parameters. It takes a response writer, where we write the response into. So that's an interface. And it takes a request structure, which has information about requests. So like what the URL was, what the method was, what the headers were, stuff like that. And then we use the helper fprintf to write a string into our writer interface. And then we just run the server on port 5000. So not too complicated. It's a very basic example. Similarly, in Python, if we use something like Flask, we import Flask. We register a handler that returns a string, so the API is a little different. And then we tell it to run in port 5000. But overall, it looks the same. Now, what if we could do this? So this is importing a module that I wrote, GoHTTP. This is actual working code. And what this does is it lets you register a handler in Python that spawns a Go runtime with the Go HTTP server and registers it on that URL. And then every request that comes in, it calls your handler in Python and back again. So how do we build this? And just to kind of look at the differences, this is the Flask version and my crazy Go version. So you could make this look exactly like Flask if you wanted to, but I think that kind of defeats the point. It's kind of a hybrid halfway point. So altogether, let's look at all the handlers. So we have the Go one that takes a response writer and a request. We have the Go and Python one, which takes a response writer and a request, and then just writes to it, calls that write. And then we have the Flask one, which just returns a string. So pretty similar. That's kind of the meat of what we're dealing with. And GoHTTP lib is on GitHub. It was sponsored by Glider Labs earlier last year because they wanted to figure out, so Go 1.5 let you build shared libraries. So you can import your code as a shared library from your Go code. And they wanted to kind of see how that would work. So this is my little proof of concept for that. So here's how we do it. We're going to export some functions from Go into a C shared library. And then we're going to write some C that we're going to be pretty sad about. And then we're going to call C from Python. And then we're going to wrap it in a Python type class that is going to make it look more or less native so we can hide the fact that we're calling C underneath. And then we're going to do a bunch of more stuff to actually make it work properly. And we're going to start from the Go side of things. So for those of you unfamiliar with Go and C Go, here's how that works. So super quick overview. In Go, you can import a C package, which is magic package. And you can literally write C code and a comment directly above it, and Go figures out the rest. Like you just build it, and Go's like, OK. And then you can see in main, I'm calling C.theAnswer. Like that's actually calling a C function inside of Go. Super easy. And now going the other way, calling Go from C, Go has this thing called export. So you go / export and the name you want to export it as in the C namespace. Of course, you have to import C to make this work. And then notice here, we're returning a C.integer. And basically, the idea is when we're exporting things from Go into C land, we want to use C-friendly types so C doesn't freak out. And this kind of bridges the gap. So Go knows about C types, and if we explicitly convert things to C types, that makes everything easier. And then we build it as a shared library, and that spits out a bunch of files. And then we write this little C file that imports libanswer.h that the previous build command spits out. And then we just call it. So not too bad, right? And we can actually use the previous method of writing Go in C and having the C call Go from inside of Go as well. But this is kind of a standalone example. Now, on the other side of this coin is the Python world. So how do we call C from Python and vice versa? We have a couple of options. There's the CPython extension interface, which works with CPython implementation. And if you've ever seen C code with like PyObject and PyModule and all those kinds of big boilerplates, which essentially you tell Python how to treat this C thing by defining all this metadata information about it, and then C can use it as a module. And then there's another thing called CFFI, which automates a lot of that. And lets you write C inline as a string and then builds it for you. So it's kind of CFFI brings the experience a little closer to what Go has natively, but it's an extra dependency you have to install. But it's really cool. Highly recommend it. So we're going to explore CFFI a little bit. We're basically defining a header up there. So C has headers, which is the signature of the function that you're defining. And then we're writing the code inline as a string. I mean, of course, this could include a file or whatever, so it doesn't have to be entirely inline. So similar, the answer returns 42 integer. And then when we call this as its own main binary executable, it generates all the files for us. It generates some C boilerplate. It generates a shared object. And then in our Python, we make a little Python answer.py. We also have to make an underscore init.py, of course. And we just import lib from that module that we just created, which is the default namespace that CFFI makes for us. And then we call it, and it works. So not too bad. A little harder than Go, but relatively straightforward. Now, calling Python from C, there's a bunch of different helpers for this. For the purpose of the stock, all we need to do, we're going to be passing a callback from Go. So we're going to, well, from Python, we're going to pass a function into Go that's going to get called every time you hit a request on that URL. So that's going to be a callback. So FFI has this helper decorator where you just define a signature and does everything for us. I'm not going to go into the details, but if you want to look at it into yourself, the docs are linked here. And you can do all kinds of other stuff as well that go beyond callbacks. In fact, there's a newer syntax now that I didn't figure out before this talk because it was too new. So before, we talked about these challenges. And now that we know how to speak to C from either end, what do we need to worry about? The first thing is, in order to overcome the different runtimes, we need to not share memory. And basically, when we pass in a memory address of something, so say we define the string in Go, and we pass it into C, and then C passes it into Python, Go has its own, it handles its own memory allocation, deallocation, so it doesn't know things are still using it in Python land, so it might free that space and reuse it for other things, or even move it to optimize it, and Python might still be depending on it, and then everything explodes. You get segmentation faults and things like that. So the trick is to not share memory. And the way we're going to do this, so here, remember, we register this handle function. And this takes two parameters. So the right one, the request, is just like a blob information about requests, about what the request looks like. And we're going to make a C-friendly data structure here, which is just like the information we need. And we're going to copy things into it. So we're going to copy the method. We're going to copy the host that called it, and then whatever else we want to include. And then instead of passing the original pointer, we're going to pass in this C-friendly copy of the data, because C is not going to mess with us. C doesn't have any runtime. So we're going to pass it through C all the way to Python, and then make sure to free it on the way back. These examples don't free things, so don't use this code verbatim in production. But you know, you're going to get memory leaks. And then the second part is the translation layer. So things like interfaces in this example. Notice how in handle func, the first thing it takes is a response writer. So that's an interface in Go. And what an interface is basically some variable that has functions on it that we know exist. So for the purpose of this talk, we only care about these two functions. Write, which takes bytes. Basically, you dump stuff into the body of the response so we can write into it. And it returns the length that you've written and the error if there is one. And the second one is actually the status code. So that should be write status, but for some reason it's write header. And the way we're going to implement this, because it's an interface and Python has no idea what an interface is, we're going to write some C in our Go that wraps all the interfacey things in something that C understands. So this basically, we're going to write these little functions in Go and export them. So let's look at the second one. It's a little simpler. Write header. All it takes is a pointer to the response writer and the header value I want to write. And then everything inside of it can be Go aware, because this gets defined in our Go code that gets exported into C. And don't worry about the parentheses and dereferences there. That's just because unsafe pointers need to be dereferenced in that way, but it's beside the point at this point. So once we get that written, in Python, it starts looking like this. So we export this into C. We import it from CFFI. And then the CFFI lib namespace, we can go see in the bottom, set status, lib.response writer write header. And that's basically starting to look like Python. And then we can wrap this whole thing in another class that actually does look like Python. So this little response writer class we create here is basically wrapping everything that's hitting the C land to make it look like Python. So we named this function setStatus because it makes more sense. Now, here's a quick overview of the entire process of translation. This is like, I found this a handy reference. So we start off with that kind of interface that has a write header thing in Go. Then we export it into a C thing that is basically a wrapper that abstracts all the Go native interface stuff. And then that creates a C header signature that looks like this, the response writer that takes integer, an unsigned integer, and another integer. And then we access it from C using CFFI like this. So just response writer, write header. And then we create another wrapper around that that just makes it look normal. That's what we're used to. Response writer, setStatus. So this is the translation layer of going from Go into Python. So imagine like you're speaking English to somebody who's Japanese, and you have a translator, and the Japanese person is reciting poetry, and the translator is kind of doing their best to get the meaning across, but it doesn't rhyme anymore. So it's like, this is what this looks like. We start off with the right intent, we have interfaces, and then we come out at the other end with something that makes sense, but a lot of the mechanics are lost in the process, which is fine for our purpose. We don't care about the rhyme. We just want to know how to get somewhere. So then the next part, turns out that a Go interface is a pointer. And in order to pass in a callback, so we're in Go land, and we register this Python handler that gets called when you get a request. And this takes a response writer that goes into Python. Python writes to it, and then sends it back to Go. In order to pass that interface, it has to cross that boundary, right? So it goes from Go to C to Python to C to Go. And we just said don't share memory because terrible things happen. And the solution is we're going to use a pattern that I've been seeing a lot since this feature became available in Go, is a pointer proxy. And that's kind of like our own little memory manager. And it's really simple. It's like 20 lines of code, barely. And it has 3 functions. You take something in GoLand, you call reference on it, and that spits out a safe integer, just an integer we can move around and share and hang on to. And then on the way back, we call dereference in that integer, and it's just a lookup. We look up what that integer means. Oh, and it's a response writer pointer interface. And then we use that a bunch, and then we free it once we're done with it. So it's basically our own really simple memory manager. If you've ever implemented an operating system, it's probably been much more complicated than this. And this is what the implementation looks like. It's just it's a locked data structure, so it's thread safe. We keep a count. Every time we put something, we increment a count so that we spit out unique IDs. And then we have a lookup from the count that we registered to the thing it's actually pointing to, and then that's it. Each of those functions is like 2 or 3 lines of code. And here's how it works. So one pointer proxy to rule them. And then in the callback, we reference to bind them. So here you see this is in Go, but we're passing this into Python. So we take this pointer response writer over there, and we reference that pointer into this opaque integer, which is W pointer, which is just like an integer thing. And then we use it a bunch in Python, and we free it when we're done. Not too hard. And then inside of our little translation layer, it's the same thing. Every time we get one of those integer pointers, we just use our pointer proxy, and we look up what that integer means, and we get the actual interface that it represents, and we use it. We call write header, because this is in Go, so we can do it. And then we return back. So nice and easy, right? So to recap, if your language speaks with C, and another language speaks with C, then they can speak with each other, or any other language, really, as long as they have a common language in between them. But going across runtimes is risky, because the memory you're sharing, you have no guarantees with it, especially since the runtimes don't speak to each other. I mean, it'd be pretty magical if they did. I wonder if there's any research on that. And then the other thing is don't share memory, of course, again. And the translation layer. So any kind of constructs you need to use between languages that don't have the same constructs verbatim, you're going to have to create some wrapper to express what you need without actually using those constructs. And of course, on the other hand, like, it's not all rosy. So you're writing C, so you're going to get memory leaks very likely unless you're very careful. In fact, there was a talk a couple of days ago about doing CPython things, and he had some useful patterns. Ross, I think, something. And then race conditions might happen because, especially in Python, you have the global interpreter lock. So any resources that depend on global interpreter lock, you might have to explicitly lock it and release it in C, which means you have to do it in Go and back and forth. So you might have to deal with race conditions. So it does get messier. And then context switching. So going from a language to C and back is not free. In Go, for example, there's a fixed number of instructions that it costs to switch from those two namespaces, depending on how you call it. And we're talking nanoseconds here, like hundreds of nanoseconds. But at the same time, if it's in a hot loop, like say you're doing it hundreds of thousands of times per request, it is going to add up really fast. You'd be better off doing it in whatever native language you're using rather than going into C. So be aware of overhead. And of course, you're touching C, and as everyone says, C is scary, and memory managing is scary, and you're going to run into security vulnerabilities. So you need to be extra double careful for that. And you're going to get architecture spaghetti. We chose that specific one because it looked interesting. Because you're moving back, I mean, even explaining this, I tried to make diagrams, but you're going literally back and forth across 3 or 4 barriers each way. And conceptualizing that can be hard if you don't isolate it properly. So make sure to isolate where this is happening and limit the damage. So for example, that little wrapper we did in Python that makes it look all native and hides all the scary bits, that helps a lot, because then anyone who's using that wrapper doesn't have to worry about those abstractions leaking. So now the fun part, now that we looked at all this scary code, benchmarks. So how do you think it did, right? So the left one is just native Go. The one after that is from Go to C, and then it's from Go to C to Python, the code just showed you. And then just for a baseline, that's GUnicorn with Flask, basically doing hello world, same thing, and Flask using the default workzerg server, which honestly, it's running concurrent benchmarks, so 10,000 requests with 10 concurrencies. So in the Python scenarios, it's probably choking on the concurrency more than anything, especially on the workzerg server, which I don't know if it's even concurrent. But you can see there's like fairly minor overhead from the native implementations at each step, but relative to the Python versions, it's still miles ahead. And I mean, this can grow or shrink depending on your use case. This is kind of, please don't take this seriously. It's literally hello world. And it's probably leaking tons of memory. And it wasn't done in it's just on my Mac while I was running Slack, so it's probably completely dominating performance from there. But it's kind of gets you the idea. So all of this is live code. You can go on GitHub, go shplib as a handy make file that builds everything for you. You just run make. And if you want to see how everything builds, go in the make file and look. And there's README, and pull requests are welcome. So as I said, this implementation is a proof of concept. It works, but you're going to have to do a lot more work to actually use this in any kind of production environment. Things like make sure all the memory is being freed. I'm not 100% sure. In fact, I'm 99% sure I'm not freeing all the memory. The API that I'm exposing is a tiny subset of the full Go HTTP server. And there's a lot more work done. So if you want to contribute to something, feel free to send pull requests to implement more of the API, make it better. I don't know if this is something you want to use in production, but some people might. And then I actually wrote up a blog post, kind of a little more in-depth version of this with the full code examples on Heroku, which is going to go live in a few hours. So if you want to reread this talk for some reason in a different tone, go there. And I'll be tweeting more. I'm using hilarious experiments. So drop by and follow me. That's it.
Thank you. Thank you, Andrey. We're going to open the panel for questions for about 5 to 6 minutes. So if you have a question, please line up to the mic.
You didn't mention one of the exciting things about mixing runtimes is signal handling. Were there any issues with that?
I'm absolutely sure there is. I mean, anything you can think of that there might be issues with, there's probably twice as many issues as you think. So signal handling, yeah, so basically it depends on which process is the main process, because the signals only get hit to one entry point. So you have to figure out whether it's going to your Go runtime or your Python runtime, whichever runtime. So, and then there's a way to force it. But yeah, I'm almost certain you're going to get signal handling issues.
Okay.
But I'm sure there's ways around it. It's just a matter of.
But you didn't encounter any in this example, though?
Depends on the platform ran it on. Control-C did stop working. So yes.
Hi. Some of these interrupt problems, like sharing memory pointers, have been solved through things like RPC or COM on Windows. Have you thought about how that would work with this kind of flow?
Absolutely. I mean, my third slide where you just exec the process and just use std out or like shared FDs across your process is a valid approach, but it's not as fun, I guess. And I mean, you do get more granular access to a whole different ecosystem. So, I mean, yes, RPC works, APIs work, microservices work, and sharing memory can work. And this is just another approach that may fit your needs better or not. And honestly, like, writing C modules and speaking other languages is useful for specific scenarios. This is kind of, it took a lot of learning all over the place to get this working end to end. So hopefully it serves as a good reference in case you need to do something vaguely similar for whatever reason.
Thank you.
Hi. So the Go interface that actually writes out on HTTP is like a buffered output on a coroutine, or a Go routine, I guess. Have you figured out like a good way to handle that over C to Python? Because like right now I understand that like it looks like the C version is waiting for the entire output to be received before it writes it back rather than starting it immediately.
Right. I mean, it's just a matter of how many of those features you want to re-implement in C in your translation layer. So we could implement like a generator in C, like a Python-style async IO generator, and then port over the Go routine, some kind of faux iterator thing that speaks to it. I totally believe it, but I didn't get that far.
Okay. Yeah, I was just wondering if like if when you use a larger data set, if you would actually see the Go version continue to stay low while the
Oh,
Go,
absolutely
yeah,
not.
okay.
No, these benchmarks were just for fun,
Okay.
and I'm 100% sure you can come up with all kinds of scenarios where they're way worse than just using whatever slowest language you can think of. Anyone else? All right.
Okay, thank you very much.
Thank you.